The topic for this morning's lecture, as I indicated yesterday, this is going to be on LOCC state discrimination. And this is the first of two lectures on this topic. Today we'll primarily be focusing on 2 qubits, discrimination of 2 qubits. Before we get into that, though, I wanted to make one point that I didn't get to on last lecture, and that is this connection between LOCC and entanglement. Okay, so you remember that just now a separable CP map, it'll take the form this tensor product form, and you're summing over it. And now, suppose that we have a system, Alice and Bob, and their initial state is a product state. Okay, so let's just say that's initialized at 0, 0. And of course, when they perform the CP map on this state, what do they get out? This will go to AI acting on 0. And BI acting on 0. Okay. So we could write this out. And actually, because this is a CP map, this will be some density operator. Likewise, this will be some density operator. And we could take the spectral decomposition of each of these density operators. And what you would have then, if we did that, we would have some convex combination. Let's call this alpha I, alpha I. Have some convex combination of pure product states. Okay, so the point is this, is the following. The first is that if you have a separable CP map and it acts on a separable state, I mean, here we just chose a simple product state, but the argument holds for any separable state. What you get out is another separable state. So the class of separable states, meaning that you can express it as a convex combination of pure product states, that's closed under separable operations. Okay, likewise, I guess you could have a bit of a converse here. Suppose you want to generate this state. Okay, so you've given me an arbitrary separable state, and we can write it in this form. And now you want to generate this state. And, well, the way you can do it, actually, you can do this using LOCC. And the protocol is quite simple. You just define a unitary. UI is going to rotate 0. We'll put A here to indicate that this is an Alice unitary. It's going to rotate 0 into alpha I. And likewise, Bob will perform some unitary on 0, and this will rotate it into beta I. And the protocol goes as follows. Alice or Bob, they generate some local randomness, pi. They look at this random variable, and they announce the value of it. And then they simultaneously both perform the unitary UI. Okay, so what happens is we can write it as follows. Pi UI, well, they act on and likewise Bob does the same thing. You see these are correlated unitaries. Let's be dagger here. Dagger Bob. And when they do this, then they will have generated the particular separable state, the target state. Okay, so this is why I think that these separable instruments that you cannot implement using LOCC are rather interesting, because we know that separable CP maps can't generate entanglement, right? So we have this, but yet if you can't implement them by LOCC, that means that you need some entanglement resource in order to implement them. Right? So if you can't do LOCC, then in order to do it, Alice and Bob need some entanglement resource in order to perform these CP maps. So it's a bit of an irreversibility. I alluded to this yesterday in the fact that you cannot generate entanglement with it, but if you want to actually perform it, you need some entanglement. Okay, so that was just that one point I wanted to say. And
These states are still non-classical.
yeah, I mean, well, so non-classical in the sense that these are pairwise not, they may be non-orthogonal.
No, I mean, what I meant was like, I mean, you start with some set of states. I mean,
Yes.
they're orthogonal states, like the one that we started with.
0, 0, right.
Yeah. Now you perform these separable things.
Yeah.
Right? Whatever you call them.
Mm-hmm.
You need entanglement to perform them, right?
Mm-hmm.
You need entanglement to perform them, right?
To do this.
Yeah, I mean, this
No, this won't. So here was a protocol right here that requires no entanglement. Alice and Bob just performed local unitaries, and each of these unitaries is going to rotate 0 into alpha I, beta I.
Okay, I'm a bit confused. So,
Okay.
so where do you need entanglement in?
Okay. So what I'm saying is that not in this. None of this you don't need entanglement. You would need it if you had these separable maps that aren't in LOCC. So remember we have this picture. We have SEP here, and then you have LOCC in here. Okay. And we'll see an example of something here that lies outside of LCC but is in SEP. And in order to implement this, if Alice and Bob wanted to do that, they would need some entanglement resource. Right.
So it is true for any separable state?
Any separable state, yeah. This.
Any separable operation? Any separable operation can be implemented by entanglement and LOCC?
Well, but sometimes you don't need entanglement, right? So if it's LOCC, if it's in.
It is out, if it is
Yes,
outside LOCC.
yes. If it's outside, then yes. Right.
But what sort of entanglement can we talk about?
Okay, that's a tough question, right? I mean, you can always fall back on just teleportation. I mean, so that sort of gives you a one. All right. Okay. Yeah.
Isn't the idea of separability that you have a common randomness source that splits the information, and according to that you do the local operation?
Yeah, that was the idea.
So why do you need entanglement for that?
Well, for this particular transformation, so say again. Sorry, maybe I misunderstood what you were asking.
So you said you need entanglement for the general implementation of a general separable operation. You cannot do it on OCC, right?
Yeah.
So where does it come from? Because to me it seems that you have a source of common randomness.
No. Okay, so when I wrote down, right. I mean, if each of these were trace preserving CP maps, then you're right. Okay, then it's just you have some source of common randomness, and then they each perform them. But that doesn't need to be the case. Remember, this could be in some big instrument where this is just one particular outcome. So,
Okay,
right.
yeah, that's clear.
All right. Now, talk about state discrimination. Okay, so the problem here is we'll just focus on bipartite systems. Alice and Bob are given some ensemble of states, and their task is to determine which state in that ensemble they were given. All right, so let me phrase that again. So you have maybe a third party, Charlie. Charlie comes along and is going to distribute a state to Alice and Bob. Alice and Bob know that this particular state belongs to one possible set. Okay, so it belongs to an ensemble. They don't know which one it is, and their task is to identify as best as possible which state was prepared for them. And so that's the goal of LCC state discrimination. Okay, so the first, I think one of the most important results it came in 2000. So this is a result by Walgate and a number of different authors, and this is in PRL 2000. And in this paper, they prove that if you have any two pure states of any dimension, so we're not restricted to qubits here, any two pure states can be, and that are orthogonal, can be perfectly distinguished by LOCC. So at first this may be somewhat surprising because these states can be entangled. And so maybe the intuition might be, well, if they're entangled, there's some sort of non-local content in these states, and that may forbid them from being able to distinguish them using LOCC. But it turns out, no, that intuition is incorrect. And okay, so we're gonna sketch the Walgate proof here. So the two states that they're gonna want to distinguish is, we'll call this S and T. And these are orthogonal states. Now, the main result of this paper is showing that there exists a decomposition for S and T in the following form. We can write, let's say this is BI. Make it clearer. This is Bob. This will go over the dimension of Alice's system. Okay, so what they show, this is what I'm writing down here is non-trivial, in fact. They show that there exists some basis, and I've just indicated it as I, choosing this as the computational basis here. So there exists a local basis for Alice, such that when you write S and T in this form, what happens is the part on Bob's side, the two parts are orthogonal. So here we have BI. These are orthogonal. Again, this is something that isn't entirely obvious, that you can actually find such a decomposition. And it's very special. I mean, this basis is special. So if you were to just choose any basis, local basis for Alice, and express the states in this, you wouldn't have this form that the corresponding parts on Bob's side are orthogonal. Is it unique? I'm gonna say no. No, I don't think it is. Yeah. Okay. Okay, so why is this helpful for the task of discrimination? Well, it gives us a protocol of how we can distinguish these states. And the way the protocol works is Alice is going to measure in this basis. All right? And this is a full basis for her state space, so she's going to get some outcome. And let's say she gets outcome I. Well, then Bob is left to just distinguish between two orthogonal states, right? Which he can always do. So you can do that perfectly. So it's a one-way protocol in that Alice first measures her system, makes an announcement to Bob, and then Bob makes another measurement, and they've perfectly distinguished between the two states. Okay, so another note is that I've written it here with Alice having this basis, but you could also find the basis for Bob. So it's nothing special for Alice here. There exists an analogous construction on Bob's side. Okay, and this is useful not only for this particular result, but in other cases where you may want to have some sort of decomposition of two states in this form for some other reason. I mean, maybe there's another problem where you want to have a canonical representation of your two states. So this is an important decomposition. All right, so let's sketch out the proof of how this works. Okay, so the first thing to know is that I want to write our state S in the following form. And likewise for T. Okay, so now here S and T are matrices, and this state phi dA, you can think of this as a maximally entangled state if we had two copies of Alice's system. Now, S is not a square matrix, right? Because Alice and Bob may have different dimensions. So S is going to be a rectangular matrix. It's going to map system dA to dB. All right. Okay. And so now there's actually no, I'm not going to choose I here because I is our special basis. So I'm going to choose another, define it with another basis. So we'll let this be alpha I, alpha I. Okay, so this is some arbitrary basis we've chosen. Yes?
In case of multi-party study, this kind of Smith decomposition is not possible, right? In that case, it will not work, right?
Okay, well, so I wouldn't refer to this as a Schmidt decomposition because the BIs themselves, if I just looked at this state, they're not pairwise orthogonal. Right, so in the Schmidt decomposition, you have each of the terms in your decomposition are orthogonal. But that doesn't need to be the case here. The orthogonality comes between the two states, right? Yeah, and so actually you can generalize this to the multi-part setting as well. And they go into the paper. So I'll direct you to there to see how you do it, how you generalize it. Okay, so we've chosen some basis alpha I here. And there's this nice property, which you can verify, that if you take any matrix A and you act on Alice's side, this is equivalent to taking A transpose on Bob's side. And this transpose is with respect to the basis alpha I that you've chosen. So this is sometimes known as the ricochet prop, or no, the ping pong property, that's what it is. Because it's like you take your A and you bounce it off, you get on Bob's side, and you pick up a transpose. Okay, so what we want to do is we want to use this on our states S and T. Okay, and ultimately what we want to do is we want to say that there exists some basis I on Alice's side such that when we perform a projective measurement into that basis, for each I, the post-measurement states S and T will be orthogonal. Right? So we want that if we look at this is, and we want these to be orthogonal for every I, right? This is sort of an equivalent statement to that. We want to find some basis I that has this property. All right, so let's just write this out a bit. This is equal to I S dA. And now we'll use this ping pong property. So this is then I S So here, the star indicates that it's the complex conjugate. Because when you're taking the transpose, you're going to inherit a complex conjugate. Okay, and likewise, on this guy, we have this T. Thank you. Thank you. Good. Okay. And now, again, we want these to be orthogonal. So what we're going to do is we're going to take the inner product of these guys. And when you do that, so taking the inner product, what we'll find is that because they're just on Alice's side is the identity, you will just get, this should be star here, T dagger S. So this is when you take the inner product, you'll get this. So this is the inner product. Okay, and you want this to equal 0 for all I. Okay, you can double check this or go through this again. But this is what you end up getting. All right. So in other words, really what the key to this is actually this matrix. This is dagger here. The key is really this matrix T dagger S. And what it's saying is if we can write T dagger S in some basis such that along the diagonals of that basis, along the diagonals of that matrix, we have all 0 elements, then we're good. Right? Because essentially these are when you contract by the two i's there, you're picking out the diagonal elements with respect to this basis. So this T dagger S is important. Okay, but what else do we know? We know that from the orthogonality constraint, from this, the S and T are orthogonal, we know that the trace of T dagger S is actually 0. So we take the trace of this, it's equal to 0. And the way you can see that is if you just remove the I here, if you replace this by the identity and then you just take the inner product, you get the trace there. So essentially what this I does is it's just picking out one particular element, the I star, but if you remove it, you get the trace. Okay. And so then the final piece then is this theorem, which they prove in the paper. And so the theorem is that for any traceless matrix M, that's actually a square matrix, there exists a unitary such that U dagger has zeros along the diagonal. Right. Okay. And the validity of this theorem is what we need, because U is basically it's going to give us our basis. U is choosing our basis. It's rotating into whatever this whatever the alpha I basis is that we represent T dagger S in, and it's giving us this particular I star basis. And zeros along the diagonal means that when we project onto I, we'll get the orthogonality. So this means this part here. Okay. So how does this proof go? Well, it's actually not too difficult to see at least the idea of it. So say proof sketch, and as an exercise you can fill in the details. Okay. Well, the idea is that this matrix is traceless. Okay. So if we look at M and we look along the diagonals, either they're all 0, which we'd be done with it, or else there would be one negative, at least one negative, and at least one positive. Okay, so we could find two elements, one positive, one negative, and then what we'll do is we'll take a unitary, and it's just going to perform a rotation on that 2x2 submatrix defined by those 2 points, and we're going to slowly rotate it such that the negative element goes to 0. All right. So we can always do that. If we have a negative and a positive on the diagonals, we can rotate it such that, I mean, we can choose either the positive or the negative, such we keep rotating it, and one will be 0 and the other will be non-zero. Okay, so we've gone from this positive-negative block, and we've created a 0. Then we continue. We do the same thing, because now we have a 0 on one of the diagonal elements, and it's traceless, so we must be able to find another negative and another positive pair. And we repeat this, and we keep reiterating this, and we do it on all these 2x2 subblocks. And you keep performing these rotations. And then at the end, you will have 0 diagonalized the matrix.
Is this true even if it's an odd number?
Yeah. Okay, because the way is you're just removing one at a time. Yeah. Right.
In the basis matrix, it need not be Hermitian, should it be?
This is anything, any M. Yeah, because this in general won't be Hermitian. This T dagger S, right?
So this is iterative, not closed form. The proof is iterative.
Yeah, I think.
Kind of algorithm.
Yeah, in the paper, I think they give it. I think they give the same iterative proof of it. Of this. Okay.
Excuse me, you just said it's not necessarily Hermitian.
Right.
So the M on the left.
Is not necessarily.
Yeah,
This is just.
so the diagonal elements can be complex numbers.
Right. Yes. Yes. Yes.
Positive and negative.
You're right. Yes. Yes. So you have. So when you're doing this unitary, right? You have to. That's an added complexity. I mean, you have to take that into consideration. Yes. Yeah. So in general, it will be a complex rotation. Mm-hmm. Okay. Okay. So this is sort of the idea behind this
What is
result here.
Complex rotation. It's unitary rotation.
Yeah.
Unitary.
Yes. Yeah.
Yeah. Okay.
Yeah. Sorry.
Not SO2.
Yeah.
Okay. So this is a general result that holds for any two pure states in any dimensions. And now I want to move on just to focus on 2-qubit systems. Because here we can actually solve the whole thing. And we can do it because 2-qubit systems have very nice structure. So say 2-qubit. Okay, so what the plan will be is we'll solve the problem for both LCC and separable operations. Yes?
So this method, if I want to extend it for more than 2 states, then the problem is you'll have to kind of demand the same thing for, say for example, I have 3 states.
Yeah,
Then I have to demand the similar kind of thing for 3 matrices.
that's right. Yeah, you would need for one fixed basis, right? Yeah.
And generally doesn't work.
No. Mm-mm. Okay, good question though. Are there any other questions on the Walgate result? No. Okay. Right. So we'll look at both separable and LCC, and this is where we'll actually see specific examples where there's this gap between LCC and separable operations. All right. And so here we're just going to focus on perfect discrimination. Which means that our ensemble states must be orthogonal. Now, we're going to consider mixed states as well, so this won't just be pure states. This constraint that our states are orthogonal, that limits the number of possibilities there are to consider, right? Because if you think about it, we're in 2 qubits, so our state space is 2 by 2, and we demand that each of the states are orthogonal. So really, there's only a finite number of cases that we can consider. And we can sort of count the different cases in the following way. So I'm going to use this notation. So it means that it's an ensemble of 2 elements, and the rank of each of the elements is 1 and 1. So this would be 2 pure states, right? Because the rank of the state is 1. So another example would be 1 and 2. So here this would be a mixed state of rank 2 and a pure state. And we have 1 and 3. And the constraint is that these cannot exceed 4, right? Because we only have a 4-dimensional space, and these are orthogonal. So we're basically looking at the supports. The supports must be disjoint, so the whole thing cannot exceed 4. So this would be 1 in a rank 3 mixed state. Okay, so I mean, I guess I'll enumerate them. So there's the 1, 1, 1 case. Well, maybe I won't enumerate all of them. 1, etc. Okay. So what we want to do is we want to basically consider each of these situations. Yes. Okay. So this is your ensemble, and it consists of, for this one here, this consists of 4 states. Each of the states, the rank of the state, is 1. So these would be 4 pure states. Yeah, is that clear? Okay. Right. So we're going to go through and pick apart all these, and we'll find that a lot of these are actually kind of simple. So the one in like the 1, 3, any ensemble where you've covered the whole space will be pretty simple. So although there's a number of them that we need to consider in principle, we can eliminate a few quickly. Okay, so that's the plan. And to do this, we're going to need some, call them technical tools. Okay, so this will be, here we're going to really write down some nice properties of the structure of 2-qubit space. And I think even if you're not really interested in this particular problem, the tools that we'll write down and play around with here will maybe be of interest in some other problem. If you're dealing with 2 qubits, these properties that we'll derive and talk about could be useful. All right, so the main tool that we'll be using is something known as the concurrence. 2 R's. Yeah. The so-called concurrence of a state. All right, and the concurrence is obtained as follows. So if we have some generic 2-qubit state, again, I want to represent it in terms of a matrix. And the way I can do that is I'll write it just like we've done previously. So here, this is a matrix. When we did R and S, we wrote S on Bob's side. It doesn't matter, right? Because we have this ricochet or ping pong property that you can bounce it off and get something on the analysis side too. So we'll write our matrix on the analysis side just for standard. Okay, and this phi plus, whenever we see phi plus, we're going to mean that it is the 0, 0, 1, 1 EPR state. All right, and now the concurrence is just the determinant, the magnitude of the determinant of psi. So this is the concurrence of psi. All right, so a bit of a few references here on where you can find this concurrence. So this first was introduced. Let's see if I have the first paper. Well, it was 1 year before the Wooters paper. Yeah, so the concurrence first appeared in a paper by Hill and Wooters. And this would have been in some PRL 97. And then Wooters returned to it a year later. And this is probably the most cited paper that uses the concurrence because he makes this nice connection with the entanglement of formation. He relates the concurrence to the entanglement of formation. Okay, but just some basic properties of the concurrence. First is that it is 0 if psi is a product state. Okay, so
Concurrence is bounded from above by 4, is it?
by 1.
No, but
So see, I have this square root of 2 here. Maybe that's where you're getting that factor 4. Yeah. You're right. Yeah, I guess if we didn't have this normalization here.
Suppose you want, if you take phi plus to be a psi, then psi is a unit matrix, right?
If you want,
I mean, if the left hand side also you want to be phi plus,
yes.
then you assign that this.
Okay. Yeah. But the determinant of it, right, is 1.
Oh, sorry.
Yeah. Okay. All right. So the concurrence has the property that C of psi is 0 if and only if psi is a product state. and C of psi is 1 if and only if psi is maximally entangled. So it's unitarily equivalent, LU equivalent to phi plus. So I'll write LU equivalent to psi plus. It also has a number of other properties. It's so-called entanglement monotone. And on Thursday's lecture, we'll talk about entanglement monotones, and we'll see that pop up there. It's also related to the eigenvalues of psi. So yeah, so if we wanted to look at the eigenvalues, this is 1 plus minus the square root of 1 minus psi over 2. Let's see if we got that right. So these are the eigenvalues of psi. Okay, those are just some properties of the concurrence. Yes? C squared, sorry. It's right there. Yeah. Yes? It gives us a way to test if it is. So we just take the determinant of this. If the determinant vanishes, then it's a product state.
What's the specialty of a PPT condition?
Sorry?
By checking the condition of positive partial transpose, you can also check whether the state is entangled or not.
Okay, well, all right. So two things. So first, the way I've defined it is we're just talking about pure states here. Okay? You can extend it to mixed states if you do this convex roof extension, which again we'll talk about that on Thursday a bit. And so there, then again, if the concurrence is 0 for the mixed states, then it would be equivalent to what you said, this PPT condition.
What is the specialty of this condition over
Oh. For 2 qubits, I mean, I guess as far as detecting entanglements, they're the same, and because the state will be entangled if and only if its concurrence is non-zero, if and only if it's not PPT. Yeah. Okay. Yeah. We'll chat at the break. Okay. So then, what we'll need is this proposition. I'll put it here. This will be the main workhorse for us. Will be the following. Okay. So this proposition, and this can be found. Well, I'll first state it, and then I'll list the references where this comes from. So let S be a 2-dimensional subspace of C2 cross C2, not of the form C cross C2, or other way around. So in other words, I don't want to consider sort of degenerate subspaces where it's something like this. So I don't want S to be the span of, say, 0, 0, and 0, 1, right? So here this is the case where Alice, her state is fixed, and Bob it's a 2-dimensional subspace on Bob's side. So I'm kind of eliminating this from the statements, this sort of subspace. Okay, then we can say the following, or C2 cross C. Okay, then there's 3 properties. So one is that S contains at most 2 product states. second property, this is a bit longer to write, but if psi1, psi2, both of these are going to be elements of S, are entangled, okay, then this operator, if we look at psi1 plus lambda psi2, psi2 is separable if and only if, I guess these are two subconditions here. So the first is psi1, psi2 inverse as anti-parallel. I'll define that in a minute. Eigenvalues. And the second is that lambda is the fraction of the concurrences. Psi 1. So this is really where the concurrence comes into play here. Okay, I said there's three things, but actually we won't worry about the third part. We'll come back to that in a second. But these are the main two things. All right, so I use this word anti-parallel eigenvalues. So this is just a way of saying the following. So you can say definition here. It's a technical idea, but it's important for the completeness of this proposition. So Z1 and Z2 are anti-parallel. If there exists some beta, and this will be less than 0, so it's some real number that's less than 0, such that Z1 equals beta Z2. All right, so these could be complex numbers, and all we're demanding is that they're just proportionate to each other by a negative scalar factor. And I mean, the first time I read this, I was like, where is this possibly coming from? But you'll see, because we're going to prove this, and it's kind of nice how it falls out. Okay, another thing is, so this psi2, I wrote psi2 inverse. We know that the inverse exists. It's invertible because we are assuming that psi2 is entangled. Okay, and that means that the determinant of psi2 is non-zero, right? Remember, because it's concurrence condition, that if it's entangled, then the determinant is non-zero, so we can invert it. So this is well defined here. Okay, so let's prove this. And again, this is going to be the workhorse for the whole discrimination problem. Okay. So first, we'll tackle the first property. Okay, so the first is that S contains at most two product states. All right, well, all right, the way this works is so any element in S can be written as, so up to an overall scalar, so up to overall factor. We can always write it as a linear combination, psi 1 plus beta psi 2. Okay? And in terms of our matrix representation, this will look like psi 1 I plus beta psi 2 I, acting on our phi plus, right? So we can look at this as just being psi 1 plus beta psi 2 Okay, so this is the general linear combination. And now what we want to do is, because we want to characterize the product states in this subspace, we want this to be a product state, right? And so what that demands is that the concurrence is 0. Okay, so remember the concurrence is just the determinant of this matrix here. So we want the determinants of psi 1 plus beta psi 2 to be 0. Okay, and well, take minus 1. Okay, well, let's factor out then the determinant of psi 1. And so then there we get I plus beta psi 1 inverse psi 2. Right, just factoring out this psi 1. And we look at this and we recognize this. So beta is our parameter here, right? And we say, this is the characteristic equation for the matrix psi 1 inverse psi 2. Actually, the way I wrote this, I kind of wrote it backwards. I'm going to just change this just because in my notes I've continued the argument in this way. It doesn't matter. I mean, I guess we could have factored out a psi 2 here, and then it would have been exactly the same. But yeah, so it doesn't matter there. Okay, so yeah, so the observation here is that this is just the characteristic equation for psi 1 inverse psi 2, right? And so the solutions to this, the beta that solve this are the eigenvalues. Okay, and so this means that the beta that solve this are the eigenvalues of psi 1 inverse psi 2. And this is a 2 by 2 matrix, so we know it has at most 2 eigenvalues, right? So that means that beta can either be beta plus or minus. And this actually proves the first property, right? Because we're saying that S contains at most 2 product states. And here, a necessary condition is that this must vanish, which means that we must choose beta such that this solution is solved. And there's only at most 2 solutions, because we're just computing eigenvalues of a 2 by 2 matrix. OK. So actually, I'll write this as an exercise right now. And it is under what conditions does S contain exactly one product state? Okay. So you can think about that. All right. So one observation that comes immediately from this is that if you have a separable state whose support is S, meaning that its eigenstates span S, then we can write that separable state as a convex combination of only 2 product states. Okay, so it's a rank 2 separable state, and we can write it as a convex combination of 2 product states. Why does that follow immediately from this? Well, because if our separable state has support on S, that means that whatever product state decomposition we give, those product states must live in S. But there are only 2 product states that are living in S, so we can always write it as a convex combination of 2 product states. So that property doesn't hold in general. The property that you can always write a separable state in a convex combination of product states where the number is equal to the rank. So here we have a rank 2 separable state, and we're able to express it as a combination of 2 product states. In general, that's not true, but it is in this case. Okay, so then let us go on to the
For a general qubit state of a separable qubit state of a particular rank,
Yeah. Okay.
rank R, you cannot write it in terms of R, is it?
No, so
Or terms?
you can show that you can always write it in at most 4. So if it's a rank 4, you can always write it in 4. If it's a rank 3, there are some that require 4, right? Okay. All right. So let's actually. So to compute our product states now, let's actually solve this. Okay, so we want to compute the product states in S. So we want this to be equal to 0. Right? So the product states in S, again, are the solutions to this. And so now we're going to use a little trick. What can I write the trick? Well, I'll write the trick down here. And this is a way to expand. So in general, if you have a 2x2 matrix and you want to write this, you can write it in terms of the trace. And it is 1 plus the trace of A plus the determinant of A. This is a little thing you can prove or look up, verify it. So now we're going to expand this using this. So we have that 0 must equal 1 plus beta plus minus the trace of psi 1 inverse psi 2 plus, sorry, maybe there's a determinant squared here, I think. Yeah, no, because it's the determinant of this, so we get a beta squared. That's right. Sorry. Determinant of psi inverse psi 2. Okay, so I've written here that, remember, we're assuming that there's 2 product states, which means that this matrix has 2 eigenvalues. We're going to call them beta plus, beta minus. And they solve this equation. Sorry. Yeah, question.
If we take the product state, then psi 1 inverse exists.
No. Okay, the product state is a linear combination of these. So psi 1 and psi 2 are entangled, right? And now we're gonna take a superposition such that when we do that, it's product. Good. Okay. And so what we found here, so this is going to be our state, and we found that the solutions, we must choose beta to be the solution to this equation here. This is just the characteristic equation. Okay. So which means that so we can write alpha 1 beta 1 as, again, up to an overall factor. We can write it as beta plus psi 2, and alpha 2 beta 2 will be the minus combination, plus beta minus psi 2. Okay? And so now if this is separable, right? So if psi 1 plus lambda psi 2 is separable, that means that we can write it as, again, a convex combination of these guys. The reason, so this equality is coming from 2 things. First, we're assuming that it's separable. So we're proving it. This is an if and only if statement. So I guess we're trying to derive the necessary condition. So given that it's separable, we want to derive these two necessary conditions. So first, we're assuming that it's separable, and which means that we can write it as a convex combination of product states. And this is coming back to what I said before. We know that there are only two product states that live in the support, so we must be able to write it as a combination of these guys. Yeah? Okay, and so now we just compare. So we just substitute this into here and substitute this into here, and we need equality here, so we derive a set of equations. So the first is that, so these imply, this equality implies that eta plus eta minus equals 1. And the second is that eta plus beta plus eta minus beta minus is 0. This is essentially saying that the cross terms cancel. So when you look at when you plug these in, you'll get some cross terms, and we need them to cancel because we have no. So this is just the cancellation of cross terms. And then the final is that. Can you guys see it down here, or am I? Yeah. Okay. So then the final constraint is that this eta plus beta plus squared plus eta minus beta minus squared is lambda. So again, this is just meaning that the psi1 component is 1. This is meaning that the cross terms cancel, and then this is that the psi2 component is lambda. Just throwing it in there. Okay. So we immediately see that because eta plus and eta minus are positive numbers, right? Because we've written it as a convex combination of product states here. So these are positive numbers. Then we see that beta plus and beta minus are actually anti-parallel, right? Because we can write this equation here. That one implies that beta plus is equal to minus eta minus over eta plus beta minus. Right? And so this gives us the first condition here. All right. And now to get the second condition, okay, it's going to take a little bit of algebra, so I'm not going to actually go through it, but I will just describe the steps because it's pretty simple. What you do is you use this equation. So this is our characteristic equation. And what you do, we want to invoke this constraint here. Okay, so we look at first this is actually two solutions. So we get one for plus and we get one for minus. So I'll just write it out, the minus one. One plus beta minus trace of beta minus squared, determinant psi1. Right, so we have two equations here, and our goal, we want to use this somehow. So what we'll do is we multiply the beta plus equation by eta. We multiply the beta minus by eta plus. We multiply the second equation by eta minus. We add them together, okay? And so we'll see that the trace term will fall out because of this equation here. Then we do the same with the complex conjugate. So we take the complex conjugate, we repeat it, and then we multiply them together. And we'll be able to use this because we'll get that when we take the complex conjugate, we'll get the beta plus magnitude squared and the beta minus magnitude squared. So again, you can see that that's a few algebraic manipulations, but when you end up doing it, you'll find that after making that multiplication, you'll get that this line eta plus beta plus squared plus eta minus beta minus squared eta plus beta plus star squared. Actually, let's keep them out. Plus eta minus beta minus squared. So this is when you, remember I said, so you do this for both this, and then you take the complex conjugate, and then you multiply them together, and then you also get the determinant. Okay, and so what this is equal to, this is just equal to, so here we look at this part here, and this is equal to lambda squared. Right, so if you square lambda, you get that that's equal to this whole chunk there. So this is just lambda squared. And now, okay, so now we use some properties of determinant that, you write the determinant as the product of determinants, and we have the -1, so that gives us the inverse of the determinant. And so this is just the determinant of psi 2 squared over the determinant of psi 1 squared. And this is exactly what we want, because this is the concurrence of psi 2, this is the concurrence of psi 1. So it gives us this condition here. Okay. So that proves the necessary condition. And for the sufficient condition, I'm going to leave that as an exercise. So I'll write out what you guys can try to prove. Right, so I guess, what do I want to say? Well, so exercise is prove the converse. And what I mean by that is if you assume these two conditions, prove that this is separable. And the hint is begin by first solving this for psi 1 and psi 2. So get some expression for psi 1 and psi 2 in terms of the alpha 1, beta 1s. And then literally just plug it in here. So when you solve that, you'll get some expression, like I said, of psi 1, psi 2 in terms of the alpha 1, beta 1s. You just throw it in there, and you'll see that with these two conditions, you get a separable decomposition. But that's something to work through. Okay. Good. So this is the main proposition we need. And I'm going to write down one corollary of it, which is also important. So corollary is that S, again, under this condition of S being a two-dimensional subspace not of that form, S has an orthogonal product basis if and only if the concurrence of psi 1 equals concurrence of psi 2 for any orthogonal psi 1, psi 2 that's in the space. Okay, so what do I mean by orthogonal product basis? It just means that, first of all, that the basis is I mean, it's what? Okay, it's a product basis, which means it's of the form 0 alpha 1 alpha prime, let's say. Okay, so it's a product basis, but it's orthogonal. I mean, sort of self-described as to. Okay. All right. So the proof for this. How much time do we have? 20 minutes? Maybe we'll leave this as an exercise as well. Yeah, well, I mean, okay, I'll sketch out one direction. Okay, so if S has an orthogonal product basis, okay, then we know that this projector, psi 1 plus psi 2, is separable. Right? This is going to be separable. Why is it separable? Because we know that if it has an orthogonal product basis, then that means that the projector itself we can write as a convex combination of this product basis, and it's going to be equal to whatever the psi1, psi2 is, because this is also a projector onto S. So we have that this is separable, and now we use condition here that lambda must be the ratio of psi1, psi2 for this to be separable, then we must have that the concurrences are the same. Okay? So that's going, if it has a product basis, and then the reverse is pretty much, I mean, the same idea. You just use this property here. All right. Now let's return to the problem.
What is the situation here? If we project it onto this two-dimensional subspace,
Yes.
is separable.
Yes.
Does that by itself imply that it had the product states in that space were orthogonal?
Yes. Yes. Yep. Again, yeah. Assuming it's not of this sort of degenerate case, right? If you're in a subspace like this, then I mean every state is a product state, right? So we really want to avoid those. I mean, for trivial reasons. Okay. So now we return to the problem. So discrimination problem. And like I said, we're gonna look at both separable operations and LOCC. So first, let's look at separable. Okay, and we're gonna break this down case by case. Remember, I said there are a number of cases, but a lot of them are the same. So we'll just look at the ones that are most interesting. So the one-by-one case, again, this is just two pure states, and we know that this can be done. This can always be done. This is always possible. And why? Because this is by the Walgate results. Actually, Walgate result shows that you can do it with LOCC, so therefore you can do it with separable, because LOCC is a subset of separable. Okay, next case is, let's go 1, 1, 1. And this is one of the most interesting ones, I think. So what we'll do is we'll actually let our ensemble, we'll denote it by, let's say, psi1, psi2, psi3. And I'm going to let eta, this is going to be orthogonal to all three. Right, so we have this three-dimensional subspace, which means that there's a unique state living in the orthogonal complement, and we're going to identify it by eta. Okay, so suppose that we have some separable POVM. It's a separable that perfectly distinguishes. Okay. Now, what does this mean? What must the pi I look like? Well, okay, so we know that we have psi j pi I psi j must be 0 when I is not equal to j. Right? This is we demand this, otherwise we'd make a mistake. I mean, we'd run some possibility of error. So whenever we have psi I, a pi I, we will only have a clique if we're given state psi I. So this implies that, and we also, of course, have that the pi I sum up to the identity. okay, because it's a complete measurement. So both of these imply that we can write pi I in the following form. This is the most general form. Be some bi here, eta, and then, well, we'll add some ai, eta, plus complex conjugate. Oops. So if I were to write this in terms of in a matrix, it would look something like 1 bi, ai, ai star. So this is expressed in the matrix representation with basis psi I and eta. All right, but there's a problem with this. I mean, the issue is that we demand that this is satisfied, and if ai is non-zero, then this will have eigenvalues greater than 1. Again, because here the coefficient is 1. All right, so we need that the ai's must be 0. So then we have this. The form must be like this, our pi i's. And you see we're kind of getting close to something like this. Right? This is why that theorem is, or the proposition is important. All right, and we also demand that the sum of the bi's must equal 1 because of the completion. Okay. But actually, we can skip right to that now. So we know that the bi must be the ratio of the concurrences. Right? So this is the concurrence of psi I over the concurrence of eta. All right, and now we just use this fact here. And so then this implies that the sum of the concurrences is equal to the sum of the eta in the orthogonal complement. So this is the necessary condition for distinguishable by separable operations. And actually, it's also sufficient, because as long as you have this holding true, you can always construct. I mean, because this is an if and only if statement, you can go back the other way. Right, so this is the necessary and sufficient conditions for distinguishability by sep. And I don't know, I think it's really interesting because it really brings together this connection between an entanglement measure being the concurrence and this task of discrimination. And it's got a nice form, closed form. Okay, so that was, I think, the most interesting. Now we got 10 minutes. Okay. So I guess because we won't have, we started a little late. I guess we can continue. So case, say 1, 2. Okay. So now we have one pure state and one rank 2 mixed state. So let's write our ensemble as we'll say psi is the pure state and rho is the mixed state. Okay, so now our distinguishing POVM. So here it was a 3-element POVM. Here it's going to be a 2-element POVM. And so I'm going to write it as so our POVM will be, say, pi psi, and then the identity minus pi psi. So this is going to click when we get psi, and this is going to click when we have rho. Okay? And you can run the same argument that we ran over there, and we'll find that actually pi psi must have the form of psi plus some b and eta. Again, eta is living in the orthogonal complement to this space. It's the same idea. I mean, really, all we've done is we've taken two of these and we've mixed them together. Right? So the notation is the same on both of these. And we want this to be separable. Okay, and so for this to be separable, there's two conditions that must hold. I erased them, but one is that concurrence of psi over psi eta must be equal to b, and of course this must be less than or equal to 1. And the other is that the eigenvalues, so this is the first condition, and the second condition is that psi minus 1 eta have anti-parallel eigenvalues. Okay, so those are the two necessary conditions. Now, this is just for separability on pi psi, but for this to be a separable POVM, we need both elements to be separable. We need this and this. Okay, and for this, we're going to use sort of a trick. And actually, this is a fact. So the fact is that if, in general, we'll say E is a rank 2 separable operator, then I minus E is also separable. So in general, this won't be true. But if E is low rank, and again, if this is 2 by 2, so I should emphasize that this is C2 that this is also true. And the reason is as follows. So if it's rank 2, what we showed is that we can always write E as some alpha 1, beta 1, alpha 1, beta 1, plus alpha 2, beta 2, alpha 2, beta 2. You can always expand it in that form. And now the thing to note is we're going to use, someone brought up the PPT criterion. So if this is separable, then I want to take a partial transpose. So the partial transpose, it's just going to take the transposition on Bob's side. Okay, so the way that if we take a partial transpose, if you haven't seen this operation before, I can talk about it maybe in the tutorial a bit more. But this is just going to give us B1 star alpha 1 B1 star plus alpha 2 B2 star alpha 2 B2 star. Okay, and the interesting thing is that actually there's a unitary on Bob's side that will relate E and E transpose. So there exists, so maybe I can write it here. So there exists a UB, so let's say this is a unitary on Bob's side, such that UB acting on beta 1 gives us our complex conjugate, and UB acting on beta 2 gives us the complex conjugate. Oops, that's squared. Okay, and again, this only works that there exists a unitary because we're only demanding that we're rotating 2 states here. If we had a rank 3 operator, then this wouldn't work at all. And I guess if you wanted to convince yourself of this, the reason is because, so we have actually that if we look at the inner products of, say, B1.
Couldn't you say that you can always find a basis such that beta 1 and beta 2 are real? I mean, which would say that they're in the equator of the Gauss field. You can always, I mean, the partial transpose refers to a basis, right?
Yeah.
So you just choose it such that E is equal to E gamma.
Okay, yeah, Right. Okay. So very good. No. That was good. That was good.
Maybe they couldn't hear it.
Okay. So what Andreas was saying is, right. So this transpose, this partial transpose, is always with respect to a basis, and so you're going to choose the basis to perform such that beta 1, beta 2 lie on the XZ block sphere. Right. So they're real in that basis. And then of course the transpose is going to be invariant because they have no complex numbers in that basis. So yeah.
Even without going to equator, I mean, since you are in a plane, if
Yeah.
you are SO2, you can do O2.
Yes.
And put the signature in the orthogonal dimension.
Okay. Yeah, that's right. Because we have a plane and we just rotate.
Only by improper rotation in a plane. But then that can be compensated by putting a negative signature in the other direction. Which is so
Okay.
that the whole thing becomes SO in SO3.
Okay. Okay. All right. Okay. Good. So then we all agree that that there exists some unitary, and so what that means then is that actually in this situation then that IE right is if we perform the partial transpose on this, so we get back to I minus E partial transpose, but we know that this is related by some overall unitary to E, right? And so we know that E, because it's separable, when we take the partial transpose, it's also a positive matrix. So therefore, this as well must be positive. Okay, so this is sort of going a long way of saying that because we know that this is separable, we also know that this is separable. And therefore, we have our element. Okay, so these are the, for the case 1 by 2, these are the necessary and sufficient conditions for discrimination. All right, and then there's some remaining cases. Oh, and I'm out of time. So maybe it's actually a decent stopping point. The remaining cases are, which I mentioned before, is when you cover the whole basis or the whole space. So if you have 1, 2, 1, and 1, 3, and also 2, 2. And so the exercise will be to determine the conditions. What are the conditions for perfect discrimination? Okay. Right. And so the reason I spent the most time building up case 1, 2, and 1, 1, 1 is when we look at LOCC, we find that there are different conditions. So on all other cases, the separable operations in LOCC have the same necessary and sufficient discrimination conditions, except for 1, 2, and 1, 1, 1. Right? And so actually, well, I guess tomorrow then we'll pick up right on with LOCC, and we'll write an explicit ensemble down where you can discriminate it by separable operations, but not by LOCC. Okay. So are there any questions on this? So I think there's 4 exercises that I wrote down. This afternoon we can try to crack them.